Good morning, all. I welcome all the participants and esteemed speaker for the second session of a NIT-sponsored short-term online course on power electronics converters applications in microgrid and vehicular technology from 20th July to 24th July 2022, organized by Department of Electrical Engineering at NIT Rourkela. I am Karthik Reddy, a research scholar at NIT Rourkela. It's a great pleasure for me to introduce our speaker now, who is going to talk to us on an advanced control strategy for EV and microgrid applications. Dr. Venkata Ramana Naik N received the BTech degree in Electrical and Electronics Engineering from Sri Krishna Devaraya University, Anantapur, Andhra Pradesh, India in 2006. The MTech degree in Power Electronics from Jawaharlal Nehru Technological University, Anantapur, Andhra Pradesh, India in 2009, and the PhD degree from the Department of Electrical Engineering, Indian Institute of Technology, Rourkela, Uttarakhand, India in 2015. He is a senior member of IEEE and IEEE Industrial Electronics Society, USA. He was joined in August 2015 and presently continued as an assistant professor grade 1 in the electrical engineering department at the National Institute of Technology, Rourkela, Orissa State, India. He is currently handling a prestigious SERP project entitled on design and control of a fast and efficient electric vehicle charger for domestic installation, which is cost around rupees 30 lakhs. Also, he supervised 23 projects for both MTech and BTech levels and is presently guiding 5 regular and 4 part-time PhD students for both academic and emerging industrial related research projects. Dr. Venkata Naik published a total of 11 research manuscripts in prestigious SCI journals like Q1 IEEE Transactions on Industrial Electronics, IEEE Transactions on Power Electronics, Solar Energy Elsewhere, etc., including reputed 4 book chapters in prestigious international level publishers like CRC Press, Taylor and Francis Group, Springer, etc. He also published 23 manuscripts in reputed IEEE national and international level conferences like IECON, INDICON, PEDAS, etc. The prestigious Ministry of Human Resource Development MHRD fellowship was received during his full-time MTech and PhD programs. His PhD thesis is evaluated with an overall A grade and received a certificate of appreciation in IEEE International Symposium on Sustainable Energy, Signal Processing and Cyber Security. He is an external for PG dissertation evaluation, technical chair in conferences, and gave many expert talks at short-term courses and faculty development programs at various reputed institutes. In addition to all aforementioned journals, he is also an active reviewer for other reputed transactions, elsewhere journals and conferences too. His research interests include various pulse width modulation techniques for power converters, multi-level inverters, and applications of artificial intelligence. Currently, he is working on non-conventional energy sources like solar, solid-state transformers for EV applications, BLDC motor drives, and hybrid electric vehicle applications. Thank you, sir. I heartily welcome you once again for this session. Over to you, sir.
Okay, thank you for your kind words and introduction. And so now actually let me share my screen. So I won't take much time because it's actually we are running over time. So yes, all of you please confirm that the screen is visible to you or not.
Yes, sir.
Yes, sir. It is visible, sir.
Yes, fine. Thank you. And so let me select the pointer. Okay, fine. So today we are, so I am going to present that an advanced control strategy for EV means electric vehicle and then microgrid applications. As we know that there are a lot of challenges whenever we are going for EV applications. As we know that EV means electric vehicle, so which is actually working on the whatever may be the source of electric source, and so that may be by means of the battery like outboard or maybe on board, or maybe so whatever may be the type of the charger which you are going to use. Even for train applications also we are using that electrical energy. And so anyhow we are using that whatever may be the machine which is actually the called as electrical machines. And so that if we are effectively utilizing the energy in various machines, like we are having that either DC or maybe the AC machines till now. However, there are some drawbacks in AC, sorry, in DC, and so we are actually switching over to the AC motors, as we know that the efficiency and then maintenance is less. And also, so whatever may be the control strategy which we are going to propose may also applicable for a microgrid applications, which is actually very important role, which plays a major important role. Like while you are even designing the filter, means we need to reduce the filter size as well. So now coming to the okay. So coming to the introduction, so here you can see that the picture of the whatever maybe the car which is going to work like a outboard charging. So we whenever if you finish the charge, and of course so you have to feed the whatever maybe the electrical supply from the whatever maybe the board, and then so the battery is going to be charged. As we know that the whatever maybe the charging condition even for a two-wheeler, so which is available in the market, so it may be taking near about that 4 to even 6 hours, depending upon the whatever maybe the type of the company. Okay, so as we are actually working on this area also, as we know that whatever maybe the charging time we need to reduce, and so charging time it takes like whatever maybe the times in terms of hours, which is actually a disadvantage. Like sometimes whenever if you want to move quick forward, and so then so it will take longer time to charge. Again, we need to move. And other drawback which we are facing, that the speed is also actually matters. So if we are actually looking into this, whatever may be the problems, and then if we are going to find that some other solutions for which, and then so our electric vehicles will move forward, and then so the demand will also going to increase in future, of course. And so now coming to the so now coming to the national electric mobility mission, like the whatever the plan is, which was on 2020, aim of improving that national fuel security through the promotion of hybrid and then again electric vehicle.
Sir, you're not audible.
So whether it is fine?
Sir, you were
Sir,
not
now
audible
it is
so
fine,
far.
sir. Now it is fine, sir. You can please go ahead.
So next, faster adoption of manufacturing hybrid and electric vehicle FAME provides that incentives for purchasing electric vehicles. Phase one of this scheme last from the 2015 to 2019. So while phase two began from 2019, is actually planned to be completed 2022. And so on 22nd May, other energy launched its charging infrastructure service in Bangalore called Aadhar Trade. So with the okay, so sorry for the distance. So other grid, so with each charging station called points. So there are companies like Tata Power.
So your screen is not visible.
Yes, students, now it is visible.
Sir, now
Yes,
it is
sir.
fine, sir.
Okay. So due to maybe some problem, I don't know what is the problem which we are facing right now. And so maybe some interruption in the internet and maybe some other issue, I don't know. And so coming to this electric vehicle scenario in India, so National Electric Mobility Mission Plan, which is actually the 2020, aim of improving the national fuel security throughout the whatever maybe the promotion of hybrid and then electric vehicle, and then FAME, which was actually the faster adoption and then manufacture of the hybrid and then electric vehicle. So there was actually a talk actually there actually no, developing the electric vehicles and then target, of course, so as per the whatever the 2022 plan. So on 22nd May 2018, Other Energy launched its charging infrastructure service in Bangalore called Other Grid, with each charging station called so whatever may be the point. And there are companies like Tata Power and so Fortune, and then other also, like even nowadays you can see that is also launched that Wagoner vehicles, as you can able to see in the outside. And so coming to the motors which we are generally preferable to use for electric vehicles, like earlier days they are using the DC series motor, as we know that the whatever may be the torque speed characteristics which are familiar to us, and so we require that a huge starting torque whenever if the whatever may the vehicle is going to start means at very beginning. So as we know that whatever maybe the passengers are actually, or maybe the whatever maybe the customers, they were actually sitting on the car or maybe the any of the vehicle, even for fraction of inflation also we require that huge torque demand. So means definitely they are going to use that earlier days DC series motor, but however there are actually some problems which are going to arise, like whatever the maintenance is requiring between the commutator and brushes, and so that is actually main drawback. However, the speed control is quite easier. So means okay, anyhow this is actually the main disadvantage. Now nowadays you can see that whatever the mixtures and the grinders are even for electric vehicle applications also, you can see that whatever may be the brushless DC motors, but however you can able to find that permanent magnet which is actually the costing of the whatever may be is going to increase the costing of the vehicle. So it depends upon the whatever may be the rating of the machine. But however, whenever if the time is going to increase, so then magnetic strength is going to be what deteriorate, so that for longer time, so maybe so whatever maybe the performance characteristics are going to be deteriorate in case of the BLDC motors. However, that it is having that good merit, like whatever maybe the power density is quite higher, and then so whatever maybe the other advantages like so it will run a smooth manner with the help of the whatever maybe the control strategy which is going to involve with the help of the inverter. And coming to the permanent magnet synchronous motor, which is quite that trapezoidal shape of the induced EMF. And so this is also more or less same as this BLDC motor, but this is only the difference you can able to achieve. But however, even here also the magnet is going to be involved. The power is what is quite lower than the whatever maybe the induction motor which we are going to use. And so in general, whenever if you are going for the power rating is quite higher, or maybe a bit more than 3 kilowatt, or maybe the near about 5 kilowatt, even more than that, of course you can able to prefer that induction motor. So whenever if you are using the induction motor, like for electric vehicles, we are having that some problems like whatever maybe the voltage ratings are different. So apart from that, other things also, like the controlling of the speed of the induction motor is also quite difficult. And other thing is that whenever if you are going for the electric vehicle, the advantage is that okay, we require that a braking system or maybe a braking mechanism. So that should be what electric braking, like whatever maybe the electric braking till now we already even studied in our courses also, like regenerative braking and then plugging and then many types as well. But however, so if you are going to implement and then so partially if you are applying the brakes, and so then so the cost of the system is going to be reduced less. In addition to that, the whatever maybe the pollution or maybe the carbon emission which we are going to face that till now, so means whatever maybe the heating effect is going to increase in the environment. So means so that is what another way of disadvantage. Once if you are using that whatever maybe the electric vehicle, so that whatever maybe the pollution is going to be reduced predominantly. So that is what the beauty of the electric vehicle. And so then so here you can able to find that field oriented control and then director control and then V by F control method. So in which we can able control the voltage and frequency of the converter, and then we can able to control the speed as the frequency is related to the speed. And so then if you are controlling the frequency, then so whatever may the speed you can able to control, like ns is actually directly proportional to the frequency, and if you are controlling the frequency, then synchronous speed is going to control. And again this ns is directly proportional to the rotor speed, as synchronous speed, if you are changing or maybe increasing or decreasing, then whatever may be the rotor speed also going to change. So either increase or maybe the decrease. So that is depending upon the whatever may be the type of application which you are going to use. Like if you want to whatever may be the speed, if you want as means if you want to increase the speed, then so accordingly the whatever may be the frequency is going to increase, and then accordingly the voltage is also going to increase. But we should not increase the voltage beyond the rated value. So we will see that one later in detail. And so, but whenever if you are coming to
So you're not visible.
Voice is also not clear.
So I think there is some issue with the network. Your screen is stuck. Participants, please wait. I think there is some issues with the network.
Okay.
దాంట్లోనే లైన్ అవుతే బెస్ట్. దాంట్లో లైన్ అవుట్లేదు చూడు మీటింగ్ దాంట్లో ఓకే సార్ ఏం కాదు. ఎస్ the screen is visible to you or not?
Yes, sir.
Okay. Actually here the network is all of a sudden it was disconnected, and then so I don't know some problem we are facing. And so out of all the machines in general, so whenever if you are going for the like near about that 3 kilowatt or maybe more than 5 kilowatt machine, even more than that in terms of megawatt range of them, like you can able to find those machines in case of the traction applications. Also really prefer that 3-phase induction motor, and so there we can able to get that flexibility of the control motor with the what maybe the available speed control techniques. Okay, so nowadays you can able to see that switched reluctance motors, which is actually simple in construction, robust ratio of the rotor is actually in general less, which helps that whatever maybe the higher accelerations, like you can able to find this type of applications in space where the speed is actually quite higher as the whatever maybe the diameter of the rotor is what as small, and so that so in these applications also of course you can able to find even for BLDC motor also, because anyhow permanent magnet is there, but the rotor size is what quite less, so that the speed is going to increase. So maybe the first as per the whatever maybe the knowledge of the induction motor, which is actually having that higher efficiency, and so as the whatever maybe the range I already told, and so but the beauty of this BLDC motor is that power density is quite higher even in case of the permanent magnet synchronous motor also, but however so which we are using that, so there is a drawback as the time tends to increase, and definitely what happens, you know, that the strength of the magnetic magnet is going to deteriorate. So that is what main disadvantage of this BLDC motor. Now coming to the next slide. So the introductions, as we told that, so the induction motors are generally used for whatever may be the electric vehicle applications, like the whatever be the advantages which we already told that weight size and the construction is what robust, and the cost is what as compared to the DC motor is low, and the maintenance is also quite low here. And so but whereas the whatever be the thing is that a difficulty in speed control, and requires that whatever may be the PWM inverter for controlling of the speed of the induction motor. So now so we need to see that, so how we need to control the speed of the induction motor, and then what are the possible methods which we can able to find till now. So like first one is the scalar control, and then vector control, and then director control. So in case control we are using here, and then so we need to see that what are the benefits which are going to improve. And so now you just see that coming to the scalar control, so how it is going to work, as we already know that, so whatever may be the scalar control which is going to control the magnitude of the voltage, maybe the air gap voltage, and or maybe the whatever be the applied voltage, and then the frequency, we need to maintain that ratio is what near about the constant. And so whatever may be the V1, and V1 is that means in general supply voltage, like in case of the transformer we used to say that V1 and V2, and so in case of the induction motor we used to say that Vs and then Vr. So that is actually the notation which we generally follow. And so we need to maintain this ratio as constant, even though either we are going to increase the voltage and proportionately we need to increase the frequency, but we have to remember that the whatever maybe the voltage should be beyond, we should not increase, means the frequency is limited. So whenever if you are going for the variable frequency, variable voltage and variable frequency control. And so then what we can say that, so whatever the EMF relay, the approximately maintain constant. Suppose if you want to control the whatever the speed below rated value, then we need to decrease and then we need to decrease the voltage. So as still maintain. Whenever if you are going to control the flex motor for below the rated value or maybe approximately the range. So what happens, right? So as we know, whatever may the supply voltage Vs is equal to the whatever may be the induced EMF E plus some stator resistance drop, whatever may be the current in the stator. So now what happens, right? Whatever may be the induced EMF E, right? So is approximately same as whenever that whatever may be the drop quite, and this drop is quite lower whenever the voltage is what rated value, whatever may be the E closer to the rated value, so the flux is maintained. And if you are lower voltage, about 5%. Now what happens? This drop is actually anyhow stator resistance and then current is how actually going to increase. So then what happens? This drop actually as drop is increasing. So whatever we what happens? This whatever will be the V by F.
Sorry to,
By F,
sir, sorry.
may not be approximately same as the supply load.
Sir, sorry to interrupt you. The in between audio is breaking. I think it is due to bandwidth problem. Can you please switch off your video so that we'll get problem solved?
Okay, so maybe
I think maybe it is bandwidth problem instead.
Okay, wait. Okay, so now it's fine.
Yes, sir. Now it is fine, sir. Please.
Okay, fine. So now we can able to see that. So as we the flux may not, then whatever torque is actually a function of the flux into the whatever current. So what happens, right? So the whatever which we generally use to drive the inverter, and so yes, something is someone is telling something, I guess. So the boost voltage is required in order to compensate the whatever the stator resistance drop. So means whenever if you are going for lower voltage, then induced EMF was low, and however the drop is also quite significant. So now we require that whatever may be the boost voltage, so that this G is what V by F ratio, and from which we are multiplying, then definitely we'll get that reference voltage and then frequency. Now if you are using that sine PWM, sine triangle PWM, and from which you can able to get that PWM pulses for upper as well as bottom leg of the inverter, which is mentioned in the figure. So now here, so in general in the V by F control, we need to maintain that slip speed is also maintained constant. As we know that whatever may be the current, stator current should be what limited. So if you are not maintaining that, and then stator current is also going to increase. That is actually the another drawback, which means that so the motor will go into unstable situation. So which is not desirable. And so coming to the and other thing is that whenever if you are going for the lower voltage or maybe lower speed control, the whatever maybe the THD is also going to increase, is because of whatever maybe the more harmonics are going to involve, and then so what happens, so overall THD is also more, and then so harmonics also more, and then heating effect is actually going to increase. So due to which again some other problems going to face, as we know that overheating of the machine, as the harmonics are more, which means the motor is at, suppose if you want to operate the motor at a rated value, means so before that rated amount of the current which is inherently you are getting, so even though if you are applying the 3/4 of the load, so means whatever may be the amount of the current which is going to be produced, so that condition is getting before that whatever may be the 3/4 of the load, means so your motor is what derated because of what heating effect, but current is overall fundamental current is less, but due to the harmonics, and then motor is going to be what overloaded. So next, coming to the vector control, like field oriented control. So how that speed of the induction motor which is generally going to control it, means so it's like it works like a separately excited DC motor, and so you just see the torque expression which is given over here is a function of that whatever may be the armature current and the field current. So in case of the separately excited DC motor, means we are speed and we need to maintain the armature current, and then we need to control the field current. So then whatever way the torque should be what we be in case of the like high speed applications, so field current should be what reduced, so that the torque in general motor torque is going to reduce. But whereas in case of the below rated speed, and so we need to maintain that field current constant, and then so we need to vary that whatever may be the armature current. So anyhow armature current is also constant for particular type of the load, and so if you are going to changing the load, definitely armature current will vary accordingly, we can able to control. But here the whatever may be the armature control, you can able to operate your machine up to the rated speed. So that we already know that how that whatever may be the armature control, like if you are changing the supply voltage, then so whatever the induced EMF is also, and then correspondingly the whatever maybe the speed is going to control for below rated speed. Now similarly, so whatever maybe the induction motor will bring, is bringing like whatever maybe the bringing like separately excited DC motor, where that we can able to find that D-axis component of the flux and then Q-axis component of the flux. So which means that so Q-axis component of the flux which is going to deal with that torque component, whereas the IDS component which is actually deal with the flux component. So means if you are going to control the whatever may be the speed of the machine for you can see that above rated speed, then we need to control that IDS component of the current, and then so for whatever of the speed, and so we need to control the torque component of the current, which is the IQS component of the current. So likewise, we are actually going to control the speed of the induction motor, but however, we require that many transformation are required, like whenever if we are actually controlling that field oriented control, like ABC to 2 again alpha beta again alpha beta 2 again TQ again rotor reference. So then there are many reference frames are required. Now coming to the director control of the induction motor, right? So in which we require the torque command and then flux command from the whatever may be the given induction motor, and then so we need to actually sense this torque and flux, and then so we are giving that reference flux and then reference torque as related to the torque is related to the motor, either a peak value of the torque or maybe the rated value of the torque. So that we need to decide, and then so as we know the torque you able to get that positive torque as well as negative torque, and then whereas the flux you can able to get that in between that 0 to 1 range only. So that's why reason we are giving that this type of hysteresis controller, and from which so based on that torque and flux error, and so we are actually framing that switching table, and based on the switching table, and so then we can able to find flux error and then torque error. So the whatever way the switching pulses are going to be generated, means which sequence should be allowed to operate for the activation of the converter, or maybe the whatever maybe the IGBT based inverter. But however here, so the problem is that so whenever if you are using that hysteresis controller, so means whatever may be the controller which we are going to use that, so sir, leave the building, sir. Huh? Okay, there is some problem over here, so all of you leave the meeting buildings. Maybe some
Please
indication.
mute yourself.
Please leave the meeting and then go.
Participants, please mute yourselves.
There is a serious problem. All of you please leave the meeting. Yes, participant. Here actually there is some fire accident. Maybe there is some problem. I don't know. Okay. And so. Yes, a dear participant. Here actually there is some problem. So which we are facing in our department, and so there is some fire accident, and so all of the persons are actually running here and there, and so maybe some problem was there here, and so what we will do, whether we'll continue or not. Okay, that I'm not. However, so we'll continue, no issue. So now it seems that okay, it is fine. Okay. And so where we are. Yes, screen is visible to you or not? Please confirm.
Visible, sir.
Okay. Okay, so here main problem of this director control is that you may face that whatever may the frequency is varied as the whatever may the hysteresis controller which we are going to use, and due to which the frequency is varying, and so it is difficult to design the filter which we are going to drive that induction motor. In between, in general, they may use the filter also, so in order to smoothen out the whatever may be the current. But whereas that induction motor itself is acting as some current filter, like that's why reason you can able to find that whatever may be the induction motor currents IA, BC, so it should be what closer to the sinusoidal, but you can able to find that distortion. But in order to reduce the distortion, people may use that filters they will use, and so whatever may be the LC filter in general they will use. But however, the inductor is inherently is there in your in case of the induction motor, but capacitive filter is required over here. So that again there means you can able to get that voltage and current should be what sinusoidal. And so again the designing of this filter as the switching frequency is varying according to the whatever may be the torque and flux error. So what happens, right? So it's difficult to design the filter also. That is actually the another problem which we are going to face, that director control of induction motor. But however, there may be options of the whatever may be the many controllers which are actually well known thing, as we already told. And coming to that proportional integral director control of induction motor PEDTC. So here we are using that PEDTC is because of we need to maintain the switching frequency is constant, so that we can able to design that whatever may be the filter in easy manner. But however, in general, our aim is to even reduce that filter, and then so to improve that current THD of the induction motor. That's actually main mode of our research. And now you just see that overall block diagram which you can able to see over here. And so here, so the induction motor is there, and then so for which we require the DC here, and so from the three-phase controller like three-phase AC, you can able to get that whatever may be the DC. So through the whatever maybe the help of the diode rectifier, and then in between the capacitor is there, so that we can able to get that DC voltage over here. And here it is a TD means TDCA means 3-level diode clamped inverter. But however, so it may also work for 2-level also. So no issue with this. Okay. And now, so before in between we are using that D-space controller. So like this space controller is going to use interface between that for power circuit, and as well as the whatever maybe the MATLAB circuit which is going to used for our application. But in between here also we can able to get the different channels like ADC and then DAC channel. And so this analog to digital converter channels are going to use to sense the whatever maybe the voltages and then current and then speed, of course. So here we are using that separately excited Otherwise DC generator we are using for the purpose of the loading. Like if you want to can able to apply that load for step load changing, for which we are using that DC generator. And then tacho generator also we are using. So for at the beginning we are actually cautious about that speed sensor and all. Later we removed also, and so it was working fine. But however, so at very beginning, whenever if you are going to implement the project, so we should be taking care of everything, and then later we can think of that removing of the sensor and all. So this tacho generator actually going to help to sense the speed. As we know that the speed tacho generator, it works like a separately excited generator. So now whatever may be the speed here, right, it is directly proportional to induced EMF. I mean, whatever the speed is what directly proportional to the induced EMF. Means as the speed is increasing, proportionally that induced EMF is increasing. So that is actually the function of the separately excited generator. So which means that, so if you are sensing the voltage, then we need to multiply the gain and through the sensor, and then we can able to extract the speed of the motor. Now, so we are estimating the speed of the motor, and then so VABC means so ABC voltage also we are estimating, and then so currents also, and so for our reference sake we are estimating the DC voltage also, and then so from which we are actually estimating the speed, and then we are estimating the flux and then torque. So all these things we are estimated, and then so from which you can able to find that so whenever if you want to operate the motor for a particular speed, we require that reference speed. And then so these are the actual values of the torque and the speed, so which we are going to generally estimated. And this SPIC, which means that speed PI controller, and then so this is what torque PI controller which we are using. And this actually the error for the speed PI controller, and then from which we can able to generate that whatever may be the reference torque, and then actual torque is going to compare, and then again so from this torque PI controller is going to generate the slip speed, and later on we are going to adding that omega r here, and then so we are estimating the theta here, from which we can able to and again so there is actually the flux controller, and from which we can able to estimate the voltages and then angle over here. And once we are going to estimate that voltage, and then whatever may be the alpha or maybe the theta, it may be depending upon the and so now if we are going to estimating the reference voltage vector position and then alpha or maybe a theta, then so you can use that either sine PWM or maybe the SVPWM or whatever may be the type of PWM you can use. Means here we are using that space vector pulse width modulation, and so from which you can able to generate the pulses. And so now this is pulses which we are going to generate it, and so it may be developed from the D-space controller through that digital IOs, and sometimes we may use that DACs also, and so these pulses should be given to the like whatever maybe the voltage source inverter which we are using. So likewise we are actually controlling the speed of the induction motor, and here you can see that like the speed type 1 fuzzy controller, and then T means torque, T1 means type 1 fuzzy controller, and so there are some other control techniques, we will see that one later. And again we are using the duty ratio controller, and all we'll see later. Okay, so now coming to the model of the induction motor, like we are using that stator reference frame, and so like we know that it's easy to frame that stator reference, because whatever may the stator quantities are stationary and then rotor quantities are rotating, and then many variables are going to be reduced. So among the various type of the reference frames, and DTC in general is used for a Stanley reference frame or maybe a stator reference frame. Hence in this work induction motor model is developed in the stator reference frame, which is actually known as a Stanley reference frame. So now move on to the next slide. And so whatever may be the dynamic modeling of the induction motor, here we are actually having some assumptions. And so the assumptions here, the air gap should be what uniform, and so that it will work like your induction motor, like a normal induction motor, and balanced rotor and stator windings with a sinusoidal distributed MMF means magnetic motive force. And so inductance versus rotor position is what sinusoidal. And so again saturation and parameter changes are in general neglected, so that so it almost works like a induction motor as per the whatever maybe the transformation event, so if you have been done. And so and whatever may be the quantities which we have been referred to the three phase to means two phase. Now here actually these are the VDS and VQS, means S refers to the stator voltages, and so D refers to the D axis and then Q axis for stator reference frame, and these are the voltage equations. And for stator reference frame, where are these actually the rotor voltages are in general zero because the squirrel cage induction motor which we are using, and so that magnitude of the voltages are zero, and so these are the quantities for rotor resistance drop, and then so whatever may be the flux linkages quantity, and then which is actually dealing with the speed as we already told. Now coming to the so if you are rearranging these equations, like you can able to find that IDS current and then IQS current and then IDR current and then IQR current. These are the rotor currents and these are the stator current in terms of DQ plane. And so whereas that side ES and side QS, and these are the flux linkages in the stator, and then side ER and side Q are the rotor flux linkages. So in which you can able to find that, so whatever may be the LS is the self inductance and mutual inductance is dealing with that whatever may be the other component. So this is what QS, so definitely it should be the other component, so IQR is going to be involved. Similarly for the DS, and then so for PSIQR, and then so psi ds. Okay, so likewise we can able to frame the whatever may be the equations. So now we just see that if you are framing the equivalent circuit in a DQ plane, so VDS, right, as per the whatever may be the expression we are framing that. So this is what RS, and then so LLS, and then LM, and again these are the self inductance which we are going to represent, or maybe a leakage inductance. And so you can able to frame the whatever may be the VDS equivalent circuit, and similarly for the VQS equivalent circuit. And so whereas that VDR is what in general 0, so which is actually shorted, and so similarly even here also for VQR. So like we can able to frame that D equivalent circuit as well as a Q equivalent circuit as referred to the stators. And so now coming to the torque expression which you can able to get over here. So as mentioned in the equation 4, and then the other expression, the mechanical torque expression. So whatever may be the mechanical torque expression is a function of the load torque as well as the inertial torque. And so in terms of mechanical and then electrical quantity which is mentioned over here. And so another expression which we are going to require, right? So whatever may be the how we are estimating the flux, right? So this is actually QS, because for the whatever may be the papers we are actually changing the notations in order to avoid the plagiarism. So means like stator rotor, either S and R you can follow, or you can follow that 1 and 2. 1 means stator and then rotor means 2, like that. That's why the rotations are different. Now how we can able to get that side ES whenever if you know that VQS voltage and then RS drop and then this current, right? So we can able to get that side QS. Similarly for side ES, once you know that, and then so you can able to find that psi S, so square root of this whatever may be the flux in D and Q axis in stator reference. And so once we can able to find that, because we require that stator flux, right? So as we already shown in the block diagram, so means this equation is required, and so this already we explained, but we require that reference flux also. How to find the reference flux? So means it's like a whatever may be the expression which we are going to follow, so which we are getting that near about that 1. Otherwise you can take that per phase voltage, and which is actually near about equal to that induced EMF. So per phase voltage, so and then per phase induced EMF, which is a function of that some constant into the frequency, and then so flux, and so from which you can able to find that flux value, and that flux will be what? So all these are RMS quantities, so you can able to get that RMS value of the flux from which from this expression if you know all the quantities. So that way also you can able to follow for finding the reference flux. And so now these are the quantities. Whenever if you know that reference flux, we are going to resolve in the DQ component. So that way we followed, and so these are a well-known thing. And so if you know that alpha and B beta in actually stator reference frame, of course we can able to estimate that reference voltage. So like magnitude of the voltage and as well as the alpha. Alpha means here you can able to treat it as from 0 to 360 degree. So it is going to vary like that. And so theta may be like if you are going to, otherwise so few books, they miss few papers, they used to follow alpha 1 from 0 to 60, and alpha 2 may be again so like 60 to 120, like that. Actually they are going to split, and why they are going to split and all we'll see later. And then so whatever may be the magnitude of the reference voltage vector, so you can able to follow using this following expressions. Okay, and so now we found vector magnitude and as well as the position over here, and so that we require the type of the PWM technique. So which type of PWM technique we generally prefer? Either sine PWM, or maybe a third harmonic injection PWM, or maybe a space vector. And so there are actually other PWM techniques. So we'll see that one later, how those are going to be helpful. So means the purpose of the PWM technique here, we are using that so to change the frequency, because the whatever maybe the speed of the motor is a function of the frequency, and also the magnitude of the voltage is also we need to control according to the whatever maybe the type of speed control which you are going to use. And so then we can able to control the speed of your machine. So in general we use that space vector PWM. So why it is so, we'll see later. The advantage of the space vector PWM, like the 6-step voltage, like whatever may be the 6-step voltage you are getting, you may get this expression, and sinusoidal PWM per phase voltage you may get this value, and the modulation index of this sine PWM in general you may get that 2/1, and so we can go for the sine PWM up to 0.786. So means so you can go the whatever may be, this is the modulation index MI. So this is what a linear range. So linear range means the speed, the whatever may be the sine PWM will give that better performance up to the linear modulation index. But beyond that also you can go. But main thing is that so whatever may be the shape of the voltage is almost like a square wave voltage. So square wave voltage means so it may be having that many harmonics. So all the whatever may be the odd harmonics, including the higher harmonics, are going to increase. So which is undesirable, because the DC quantity is going to appear in the AC side as well. So due to which more lower order harmonics are going to increase. So there may be the fundamental attenuation of the fundamental is going to take place, and then so more switching losses, and so on the ripple or maybe the harmonics are going to increase. Okay, so now in general we want means beyond this modulation index, so we can't use this sine PWM voltage and sine PWM method, and so that's the reason. So okay, that's the reason we will go for the space vector modulation, and in which you can able to go for that whatever maybe the modulation in the linear modulation range should be what more than this way, so that we are going to we are actually effectively utilizing the voltage. That's actually the beauty of this whatever may be the space vector PWM. But however, that another method is also there, the third harmonic injection pulse width modulation. But however, so with the help of we should get that higher amount of the voltage. But index increase means we are okay. These are the yes, students, whether my voice is audible to you or not? Please confirm.
Sir, now it is fine, sir.
Okay. Actually, in between, actually there is an interruption. Yes. Okay, fine. So now the disadvantage over here that so whatever maybe the switchings will be what more, and so how the switchings will be more and all we'll see. So how the switchings will be less in case of the space vector modulation we'll see over here. So this amount is remains same, means whatever maybe the linear modulation range will extend up to 0.907, and so this point is actually still continuing, and lower ripple compared to the sine PWM. Okay, we'll see that one, and then so lower switching losses compared to the sine PWM or maybe third harmonic injection PWM, because single switching transition takes place for each vector movement. This is actually the beauty of this space vector PWM. Whenever if you are using means okay, only one leg is going to be operated from one switching instant to the another switching instant. That is actually we'll see that one later in detail so that we'll understand. So it is actually best suitable for either director control or maybe even vector control also. So because the whatever the switching transitions are less, so we may expect that better performance like whatever maybe the THD and all. So we'll see later again in detail. Now coming to the two-layer inverter of an induction motor drive, actually framing that whatever the inverter should be like sometimes there may be connected to the upward or maybe the bottom side, bottom side of the DC, right? So we are actually reframing that whatever may be the inverter in a simple manner, such way that you can able to understand in better way. Like you may get that A phase, B phase, and then C phase, and so then like you may get the different possible switching states. Like we are having that. Three phase and then so this is a two level inverter and then three phase, so total you may get that eight possible switching states here you can able to get. And so what are those possible switching states you can see here. And so like if it is about 100, which means that so first A leg should be connected to the positive and then whatever may the 00, which indicates that B and C should be what connected to the bottom leg of the DC source. Likewise, even here also V2 means the states are 1 1 0, which means that so first two legs should be operated switched to the top leg, and then so remaining one still C is to continuing in still in C state. So likewise, similarly V3 means 0 1 0 means 0 1 0 means so now whatever may the first leg should be what shifted to bottom side, and then so B is what still continuing, and whereas the C is what actually still in a like the negative side of the DC. Likewise, we are actually framing the whatever may be the sequences like you can able to observe here means total 8 switching states like this is what V1, V2, V3, V4 and V5 and V6. These 6 are the active states of the vectors. Why it is called as active state of the vector, we'll explain later. And then so these are actually the zero vectors, or you can say the null vectors. Okay, so null vectors. So we'll see that one later. Means in which you can able to find that either a line or maybe the phase voltage 0. So that's the reason we used to call it as these are the what or maybe null vectors, and so active state vectors in which you can able to find the either phase or maybe the line voltage, line to line voltage. So you may expect that whatever may be the voltage is what the concerned magnitude is what fixed. We'll see that one later. So in the next slide. So now as per the whatever may be the switching position, we have been developed that for calculation of the VAB and then VBC and then VC. These are the line voltages, and similarly the phase voltages for the inverter. And means instead of using the inverter, we can frame the inverter by ourselves with the help of the modeling equation. Like that, we used to follow this formula. And then so finally we are getting that all these line and phase voltages. And similarly for the some of the either line or maybe the phase voltages, of course you can able to use this formula, and so that you can able to calculate that sum of the line and phase voltages as followed the whatever may be the expression. Now if you are looking into that whatever may be the block diagram here, from which you can able to find that V00 means all are 00 means bottom side it is connecting, which means that minus VDC by 2 and minus VDC by 2 and then minus VDC by 2. And so VA0 means is actually the pole voltage. So the difference between the pole voltage means, so if you want you can go back to the whatever may be the circuit diagram. So pole means so between these two. So between these two we used to call as a pole voltage again. So again B pole voltage means B2 this O. Again C pole voltage means C2 this one. And then so phase voltage means the corresponding phase of the whatever may be the induction motor from means corresponding A to N. So this portion we used to call as a phase voltage. However, so you can find some mismatches in the papers. They are going to confuse. Sometimes they used to mention in the papers also pole voltages also same as that phase voltages and phase voltages. There is a confusion, but we try to avoid that. But however, that may be again depending upon the construction of the motor, either star or maybe the delta. So now for the first case, V00 means all are connected to top side, means all are sorry, not top side, bottom side. So you will get that minus VDC by 2 minus VDC by 2. And so Vn0 means if you are actually doing the sum of the all and then divided by the whatever may be the respective numbers, average value, you will get that. This is what common mode voltage we used to call it, common mode voltage. And so now you just see that whatever may be the VAB, VBC, VCA, these are the voltages, you will get that 0.
We request participants to please wait for 1 minute.
Yes, actually, what happened, all my esteemed participants, just for announcement that in our department means electrical and just for a moment.
Arnab. Hello, Arnab. Okay, fine. So actually now we are using that mobile net. Okay, so So as we are having some problem in the department, so now we are switching over to the mobile internet. So please wait. Yes, screen is visible to you or not? Please confirm that.
Yes.
Okay.
Yes, sir. It is.
Thank you. So now you just see that whatever may be the voltage vectors, like for different states, like 0, 0, 1, 0, 0, and then 1, 1, 0 again, different states. So means from V0 to V7, in which V1 to V6 are the active state voltage vector, as I already stated, in which that you can able to find that whatever may be the voltages, some of the line voltage or maybe the phase voltages are you are getting properly. So that's why reason we used to call it as these are actually the active voltage vectors, whereas the V0 and V7 are actually the null voltage vectors, in which the line voltages or maybe the sum of the line voltages also going to 0 and phase voltages also. But as compared to this, whatever may be this voltage vectors, you just see that the angle, the magnitude of the voltage is what fixed. You just see that magnitude of the voltage is what in general you are getting the fixed value, but however these are actually the displaced by an angle of 60 degree. You just see that 60 degree means first vector V1 to V2 is what 60 degree, again V2 to again V3 is again 60 degree delay. Means now we are framing that whatever may be the vectors vector notation by whatever may be the mentioning the all the vectors. So however we also going to note that, so if you know that VAB is the what let us take whatever may be the state 1, 0, 0 state. So this is what 1, 0, 0 state. So due to the whatever may be the problem of the MS team, so maybe it is actually overlap, no issue. This is about 100 in which that the top side is connected to positive DC, whereas B and C are connected to bottom leg, so in which that is so negative DC. So now you just see that VAB means VDC, and then so VBC value is 0 and then VCA. Now we need to find that V1 vector, which means that the corresponding phase voltage vector, and now we are actually framing that VAB, VBC and then VCA voltage, and now we are finding the position of the V1 vector. Similarly for other vectors, if we are finding means as per the whatever may be the phasor representation, so we are framing that voltages V1, V2, V3, V4, V5 and then V6 all are actually displaced by an angle of exactly 60 degree duration. You just see that 60 degree duration from here V1 to V2, V2 to V3. But whereas that V0, V7 are actually the null voltage vector which are going to represent that origin of the vector. Now if we are actually resolve that whatever may be the alpha beta axis in this fashion, now we need to find the reference vector, and then so assume that if your reference vector may be sitting in some so and so region, but here we need to identify the means we need to frame that sector numbers. So means we are actually what framing the sector numbers over here, right? So like we are having total how many sectors? So total 6 sectors. So 1, 2, 3, 4, 5, 6. So means each sector consisting of the angle of 60 degree. Right. So likewise, we are actually framing the vector. Now, if you are maybe looking at the reference vector at some so and so place, and now we need to find that whatever maybe the switching times for the different vectors also using the space vector PWM. Okay. So now assume that if your reference vector may be in a position of in this place, now we need to find that. So the V1 vector should be operated at how much time, and then V2 vector is operated at how much time, and then so 0 vectors. We are also having that 0 and 7 vector. Means V0 and then V7 vector. So means we need to identify that, and as per that whatever may be the space vector principle, so we need to operate the switching movement from one vector to the another vector in a sequence manner. Let us consider that V0 I have been considered, so V0, so this may be a first case, and then so next I may be consider that this is actually V1 will be the second case, and again so I may be consider this the third case will be the V2, and last I may be consider that V7 vector. Means now you just consider that 1 to 2, so only one leg movement takes place like V00, and then so here is what 100 means now what A phase should be what higher, and whereas that B and C are still in a lower side, means which are connected to bottom side of the whatever maybe the DC or maybe the negative side of the DC. And few papers they used to follow that 100 is actually going to means follow like plus minus minus also. Means plus means in general it is going to connect it to positive side of we can see that DC. Okay. And whereas the negative means negative side of the you can say that DC like that. So we need to remember. And so means they used to follow the notation like that, but don't be confused by means changing the means one paper to the another paper. And so now we frame that whatever may be the vector in this fashion. Now we need to find that whatever may be the switching times for this case. Okay, now we will move on to the next slide. And so this information we already explained. And so now here we need to find that switching times of the T1 and T2, and then we need to find that zero switching time also. Okay, now according to the whole second balance principle, so we need to resolve that whatever may be the vectors on alpha axis and as well as the beta axis. So now if we are actually resolving the vectors on alpha axis as well as beta axis, so you may get this whatever may be the expressions. So let us take this maybe the one expression, and this is actually the second expression. So the second expression here, which is going to tell with the T2, which means that V2 vector, the magnitude of the V1 and V2 vector are actually same. So that's why reason we are keeping that 2/3 VDC and then so V1 vector. So as this V1 vector is lying on the already on alpha axis, as this is already lying on the alpha axis, what will be the V1 component on the beta axis? Definitely 0. As this component is 0, now whenever if you are operating that V2 vector, then assume that there may be the some time T2, and then so now the whatever may be the V reference vector, so which is actually lying on the beta axis component, this V reference vector which is lying on the beta axis component, means you may get that second expression. Means if you are solving the second expression, so you may get that T2. So let us take this maybe a third expression. Now we like whatever may the first expression, how will get this whatever may the first expression, this first expression. So when the quantities are lying on the alpha axis, so all the quantities are lying on the alpha axis, so which means that so during that time you will get that V1 into T1, right? And whereas that this V2 you may get that 2/3 VDC into cos 60 degrees, and so during the time T2 is there, and so anyhow this is actually the reference case, you may get that whatever may be the TS and all. So means if you are solving this, so means you already know the third expression. So now if you are substituting the third expression in the whatever may be the first expression, because so in the first expression, so we need to find the T2, then only we can able to find the T1 in terms of the TS. So means now we can able to get that T1 expression by substituting the whatever may be the T2 means the T2 expression, which means that third expression in the first X. So then what happens? So if you substitute the 3 in 1, and now you will get that T2 expression. So now finally you can able to get that TZ means zero switching instant of the time. So then you can able to get that zero switching instant. So means how you will get that? So you already know the T1 and then T2, and you please subtract from the whatever may the TS to this, and you will get the T0 time. So that way you can able to find the time using that whole second balance principle in a you can say that average fashion. And so in different way also you can able to find, so V reference vector and then alpha, and so which is multiplied with the TS, so as but whatever may be the reference, so magnitude is what 2/0 degree, and so T1, and so V2 vector is what again 60 degree. So from which if we are actually means separating the two quantities like real and imaginary quantities separately, and then if you are solving, then you will get the again so same expression. So that is up to you in which way you are going to follow. But here, so whatever may be the equal division of zero vector time is important. So not more than the 3 switching states, and the final state of one sample must be the initial state of for the next sample. So in order to obtain the minimum switching frequency for each of the power devices, the states sequence is arranged in such a way that the transition from one state to the another state should be what followed only one leg, as we already told. So now this is the algorithm which we have been used in the M-file programming in the MATLAB. So we need to initialize the whatever maybe the values like TS, TES, and then alpha, and then so actual clock time, and then so switching states of the whatever may be the sequence, and then we need to find that whatever may be the T1 and T2 as we found for the second means for the first sector. Similarly, we need to find that TA and TB means expressions you may get the same in the other sectors also, but there is some difference. So that we need to identify. And now as per the whatever if n means sector number, so where n we used to represent the sector number as per the sector number. So if it is an odd number, then we need to follow this sequence. And so if it is about even number, so we need to follow this whatever maybe the alpha f should be pi by 3 minus alpha. Here assume that this alpha is actually alpha f is what in between that 0 to 60 degree. So whatever, because either in a first sector or maybe the second sector, the duration between the active vector or the angle between the active vector is what in the range of 60 degrees. So that way we used to follow, and so total sequence we have been developed. And if it is a n is equal to 1, so we need to follow the sequence 1 and then so sequence 2 and then sequence 3, like up to we can able to get that 6 sequences. So which are going to be implemented in the M file programming. Otherwise you can use that logic code also. But however, you can look into that how that actually the actually looks like, and you just see here. And for the first case, when the vector reference vector is sitting in the sector 1 region, right? So in this region, as I told that we need to first operate that V0, right? So V0, V1, V2, and then V7. Again, so again it should be what reverse in the in a like one leg movement only, like V0 means 0 0, again 1 means 1 0 0, again 2 means 1 1 0, again 7 means 1 1 1. So up to it's okay, clear. So means okay, this is what 7 is continuing, means afterwards which vector should be operated in the same way, same sector. Now again it should be what 2 should be operated, again 1 should be operated, again 0 should be operated in order to operate minimal switching transition. So that way we are operating the whatever may be the space vector. So like whatever may be the sequences we need to follow for first half of the sequence and then second half of the sequence. Just see that whatever may be the vector movement takes place from one position to the another position, only one leg is actually moving. So that is actually the beauty of the space vector modulation. That's why reason we used to say that the switching losses are going to reduced as minimum as possible as compared to the other PWM technique, in which there you can able to find that different like whatever maybe the at each movement like, so you can able to find that 2 switches may be changed, or maybe even 3 also for some time. So means that may not be takes place over here. That is actually the advantage over here. And so this is actually the transfer function which we found that in case of the PIDDC of the induction motor, and so the whatever may be the GFS, and then so we found the closed loop transfer function, from which we found that whatever may be the K value, accordingly we are actually using that whatever may be the same, means not same value, because we are actually linearizing the network as that induction motor, and again whatever may be the inverter. So these are actually the non-linear elements. So means we are making that linearizing, and then we found the transfer function, and then so we found the closed loop transfer function, and so in which we are varying that Kp and K values, and then we found that stable system, and then whatever may be the phase margin and then gauge margin. So accordingly we can able to set the Kp and K values from the whatever may be the border plot. And so but we need to see that stable, whether your system is stable or not. In between those range of the KPK values, if you are changing, but of course so your system will get stable, means so you will get that performance in better way. Otherwise so sometimes so will be better and then sometimes it may not be better. That is the problem in generally we are going to face. Now we are going to moving on to the fuzzy logic controller. Why it is so required? Because as we can see that whatever may be the past experience, so it may be consisting of many equations and many mathematical analysis are required. But here, whenever if you are going for the fuzzy logic controller, right? So no need of very big complex equations. Uses only simple logical rule. But whenever if you are using this logical rule like if, then, and, or not rules, and so we should means aware of the system. We should study the complete system, and then so of course we may apply the fuzzy logic system also. And so it may be effectively deals with that non-linear control system also, even either means linear as well as non-linear also. But we should actually first thoroughly looking into the system, and then so we may use this whatever may be the fuzzy logic system. But it may be requires that expertise person so to design the whatever may be the controller. But in case of the fuzzy logic controller, there are actually the many classifications which you can able to find over here. So like type 1 fuzzy logic controller, and so in which you can able to find the neuro fuzzy or maybe a neural network. So again recently you can able to find the type 2 fuzzy logic controller. Here we are using this type 1 fuzzy logic control 1 and then 2, and in which we are using that Mamadani type, and then so Sujina and Sukumato. So these are methods also available, but however we are using that Mamadani, so which is actually getting the better results, and so in which we can able to get that center of set value or maybe the centered value. So as per the whatever maybe the formula which you can able to see in the later slides. So now, in order to improve the performance of the dynamic performance of the induction motor drive, so one thing is that flux means the whatever may be the ripple quantity we need to improve, for which we require that whatever may be the duty ratio controller, in which that whatever may be the current THD can be improved. We'll see that one how it is going to be improved, and so again if we are further using that hybrid different possible duties, and then so there may be the chance of improving that flux ripple. And so if you are using that whatever may be the PI controller are going to be replaced with the whatever may be the fuzzy logic controller, so there may be a dynamic improvement. So as we know that whatever may be the PI controller, the KPKI values are going to be fixed, and so that values may not be the means we are going to fix the value, but sometimes whenever if you are changing the speed, and there may be slight error in the speed also, and so means the if you are maybe properly doing that whatever may be adjusting that values during that operating time, and then so your performance will get better, and so that whatever may be the peak overshoot and all is going to be even minimized with the help of the fuzzy logic controller. Even in the PI controller also it can be done, but some extent it can be done, but so beyond that, so if you are adjusting that, again steady state performance may also going to deteriorate. So now in case of the type 1 fuzzy logic controller, as we told that if then under rules we will use, it is actually a simple process in which we can we are having that crisp values, right? And so input is a crisp value, again it is converted to the fuzzy, and in between that you can able to get that rules like if then rules in the fuzzy logic control system, and again there is a defuzzifier which converts the fuzzy values to crisp value, which is actually the actual useful value, whereas the crisp value here which is going to deal with the error, and then so this may be the whatever may be the output of the respective of the controller. And so but here as we can see that how we can able to use that if and then rules we'll see later. Okay, so in case of the whatever may be the process of the fuzzy logic controller, you can able to find that fuzzification process, inference engine, knowledge base, and then defuzzification. This is already we explained, because inference engine and knowledge base is consisting of the if then rules, and whereas the fuzzification which is going to convert that crisp value into the fuzzy values, and finally defuzzification means again it is converting into the again crisp value, which is actually practical value. So as per whatever may be the rules which we are going to be designing now. So okay, we studied some whatever may be the study, but main thing is that how we can able to apply. Let us take whatever may be the PA controller, like which is a function of that proportional controller and then integral controller. Now, so if you are doing that differentiation in the both sides, so you can able to get that whatever may be the output. So that may be what change in output you can able to expect. So that change either it may be good or bad. So that we need to decide. So that's why reason we require that whatever may be the error and as well as the change of the error for the input of the controller. And then so now so we need to decide that whatever may be the membership functions. And so which type of membership functions also useful, like there are again many types of the membership functions like triangle, again trapezoidal and Gaussian and all. So we need to even justify that which type of membership functions we need to use. So now you can see that the whatever may be the this is centroid method. Okay, so we'll see that membership functions first. So here we are using that triangular membership functions. As you can see that whatever may be the torque performance, like it almost the shape is almost like in this fashion, and that's where reason torque speed characteristics like this fashion. So means we used to follow that triangular membership function, but at the end we are using that trapezoidal membership function so that we can limit the whatever may be the range of the respective of the controller. So now you just see that whatever may the calculation of the centroid. So as we need to follow the whatever may be the as following the whatever may be the expression in which we need to sample the whatever may be the aggregate output membership function means, like we need to again give that output membership function, and then we need to find that crisp value of the output by following this expression, which is actually well known thing for us. And so now the advantages is that it's easy to implement. And so in the MATLAB, so either you can write the program or you can able to frame the rules by opening the blocks and so you can do. And so it has a single membership function only. So you can, as you can see that the membership function, so like any of the membership function if you are selecting, so which is what single membership function. It is only suitable for lower footprint of uncertainty of the system, and so not suitable for large footprint of uncertainty. And so we'll see that how it is maybe not suitable for a large footprint of uncertainty. So we'll see that one later. So now we frame that whatever may be the speed type 1 fuzzy logic controller for different membership functions like negative big, negative medium, negative small, and again 0, positive small, positive medium, and then positive big. And similarly for the output side also we are actually framing. So these are the actually crispy value. So whereas the actually these are the errors, change of the errors, and then so finally you can able to expect the crispy value of the output in the respective of the controller. So as for we followed that if then rules as following the table, and so this is actually the surface viewer from which we can able to find the information like where to where your actually flux is going to sorry, if not flux, this is actually a speed type 1 fuzzy controller, so how it is going to vary, so we can look into that also. So similarly for torque type 1 fuzzy controller which we have been used, and so as we followed that means a bit similar to that whatever may be the case, but here you can able to express that whatever may be the slip speed is what different, but we are making in a per unit system such a way that so there won't be any problem at all. So now in case of the type 2 fuzzy controller which we are going to use for controlling of the speed of the induction motor, it effectively deals with the huge ambiguity data or maybe the whatever maybe the huge footprint of uncertainty. It has two membership functions and with the three-dimensional control. How it is we will see later. It has the advantage of both the type 2 reduced set and as well as the type 2 fuzzy set. And so here also we are using that Mamadani method, and so as it is actually consisting of simple rules. Now you just see that. So as you just see that, what is the difference between the type 1 and then type 2 fuzzy set? You just see that in general this is actually the whatever may be the type 1 membership function, and so in between you can able to expect that so we are actually again keeping that some blurred area, so which is consisting of again two membership function, which that's why reason we used to call it as a type 2 fuzzy. And so this is actually dealing with the two-dimensional, and then again this is actually the one more membership function is added, which means that it's a three-dimensional control. So now if you are actually keeping that, let us take this is actually the crisp position, so either error or maybe whatever may be the control variable which you have been used. Now you can able to expect that whatever may be the membership function for the type 1 fuzzy, the fuzzy value you may expect in this range, whereas the type 2 fuzzy so means in this range you can able to expect. Likewise, so it may be varying. So means we need to define the cost effective function such a way that so it may be give that better performance, either if you want to concentrating on the torque controller or maybe the flux controller. Okay, so that is actually going to depending upon the this whatever may be the control technique. So means you can able to expect the different fuzzy value, so that whatever may be the crisp value in the output side is also going to different, like whatever may be the error and then change in error, and so whatever may be the controller, so in the output you can able to express. So for which we need to actually design the controller, we have to write the program and then implement, and then we need to run, and then accordingly we need to develop the whatever may be the membership functions. So now if you are looking into the overall process of this type 2 fuzzy, means which is almost same as the similar to that type 1 fuzzy, but here you can able to find that reduced fuzzy. So in order to get that actual value of the crisp in the output side. Now you just see that these are the change in error and then error from which we are actually, this is what output membership function output side, and so from which we are actually having that some shape of the whatever may be the fuzzy value. Again this fuzzy value is going to convert it into the crisp value, and so we need to find that left side and then right side of the whatever may be the respective of overall membership function. So we need to find that cost effective function or maybe the center of set value. So from which we need to find that average value for the whatever may the respective of the controller. So TL TL means left side of the torque, and then so TR means right side of the torque. So likewise we are actually doing that controlling of the membership function, and then finally so it is actually going to give that required value of the torque. So how we are actually developed in the MATLAB means, so we are actually embedded as we follow the different type 1 means different combination of the membership functions, and then we frame that means aggregated membership function, and then so we used to follow. Even people are doing for n types of the membership function, but we used to consider that these two cases, so that we'll see that okay whether we are getting that better performance or not with the help of this artificial intelligence technique. And this is the whatever may be the process, as we already told, for whatever may be the 7 membership function which we have been used, and the same process we are actually estimating the whatever may be the torque in the left and right side as following the whatever may be the procedure. Okay, so with the help of this, okay, we are actually estimating the value of the crisp value in the output side. So okay, it's actually repeating. So now, so this is what the membership function which we have been framed. After framing, you can able to find this type of membership functions, and then so you can able to see that this is what change in error, and then error for the S means speed, actually suffix S means, and so the speed PI controller output is what torque controller, and so this is actually the fuzzy value. And so now we can see that the whatever may be the surface view of the fuzzy controller, and similarly for the other case. And so now you just see that we need to actually looking into that flux ripple also, whatever may be the like in order to improve that ripple performance or maybe the current ripple performance, right? We need to find that error of the voltage vector. So we are also taking care of that, and for which so we used to follow again volt second balance when the vector is actually sitting on the reference vector means in the sector 1 region. This is what sector 1 region. In the sector 1 region, so we are finding the error voltage vector in both the D as well as Q axis. So for which, so along the whatever may the for which you just see that we are getting that D and Q1. How you are getting that? So let us take, so whatever may be the V1 vector is here. So now V reference vector is here. Now whatever may be the Q axis, we are assuming that it is actually lying on the reference vector such a way that what happens, so some variables are going to be reduced so that it is easy to calculate the flux ripple also. Now, so for which, okay, if you are actually resolving the vector on the V1 vector, right, along with the V1 vector, then you can able to get the D vector and then Q vector. Similarly, for the whatever may be the along the V2 vector, so you are getting the again D vector and then Q vector. So means you are getting the D component and then Q component. Similarly for the D component and then Q component. And this whatever may the ripple jet vector, right? Qz, how you are getting? So means this is about 0 vector and this is actually the reference vector. So definitely you will get the negative value here. So means we reference into Tz value. Means Tz means 0 switching time. So you will get that Qz value. Now, if you are after resolving that, now if you are actually framing that Q-axis ripple vector in a different way, and then D-axis vector in a different way, and then so if you are actually finding out the whatever may be the resultant value, right? So you will get that resultant flux value. Okay, somewhere else. So this way. So here, so if you are actually solving the whatever may be the flux ripple vector, so means finally you may get this expression for the space vector PWM. Now similarly for other sequences, okay. Now for similarly for other sequences, what we have done that, so we actually followed the same way, but now what we have done that, so we are actually finding the different sequences. Space vector PWM, like for a given sector means we used to follow 0, 1 to 7 switching states again, so it may be repeated 7 to 1 0. But whereas we need to actually looking into that some other sequences such a way that we need to find that, so how we are getting that performance, we need to looking into that also, for which we are following that whatever may be the rules and regulations like this fashion. The active state 1 and then active state 2 must be applied at least once in a subcycle. So means for a whatever may the subcycle, given a subcycle, only at least one time these two should be operated. Next, either 0 state or maybe the 7 state, means 0 or maybe these are the null state must be applied at least once in a subcycle. That is also important. So that way we need to actually develop other sequences. In case of the multiple applications of the active states, like whenever if you are using that 1 or maybe a 2 or maybe again, so you are using both. So the total duration for which that active state is applied in a subcycle must satisfy 2. So 2 means either 0 means either means repeatedly if you are using 1 or maybe a 2. So during that time, so at least one time you have to use the 0 or maybe the 7. So again the total duration for which the 0 vector either using 0 means 0 state or maybe the 7 is applied in a subcycle must satisfy again 1. So like in which we can able to find that 1 and 2 vector. So only one phase must be switch for a state transition, means for every moment, as we already disclosed, one switch should be moved. The total number of switchings in a subcycle must be less than or equal to 3. So we are following that. So less than or equal to 3 switching states. Now, so coming to the volt second balance, as we coming to the sequences as per the whatever the rules and regulations we framed in the previous slide. So now, so we started from the 0, 0, 1. Okay, means 0 to 1. Okay, anyhow, single movement takes place. Again 0 means 0 state is what repeated, which is not a valid state. Again 0, 1, 2 means okay, 2 vectors are coming and anyhow null vector is also there. So this is valid. Similarly, for other cases also, like we are actually finding the different valid sequences. Even here also 1, 0. Again 1 we have been started. Again 0 means 2 is not operated, so that this is not valid. And so 1, 0, 1, 2. Okay, anyhow 1 is repeating, but however, means these two active vectors are there, but 1 is repeated and 0 is also there. So this is also valid. Like that we framed that different sequences. And so even here also whatever may be the valid sequence. So again 1, 2, 1, 0. And so this is actually not valid, again valid. So likewise we framed that whatever may be the different sequences. And so like finally we got that sequences in a first sector like conventional space vector, that's what 0, 1, 2, 7, and then clamping sequences which are actually 0, 1, 2, again 7, 2, 1. Again special sequence type 1, right? So 0, 1, 2, 1, 7, 2, 1, 2. Like we finally got that 7 sequences. So in a 7 sequences in a sector 1. In a sector 1. Okay. So means now we need to look into, we are having that multiple options, but we should sure that whether if you are using something means okay, you are getting the better performance or not. We need to look into that as well. Like we 0, 1 to 7, like space vector we already know, and so clamping sequence. So we need to follow like 0, 1 to 7. So you just see that switching movement even here also 0, 1 to 7. So 0 to 1, again 1 to 2 means only single switching movement takes place. And again clamping sequences, these two 7 to 1 and again 2, 1, 7. So again single switching movement takes place. Likewise for all the sectors we have been mentioned, but so how that actually the differences we can able to observe, like space vector you can able to expect this type of PWM. Like whatever may be the case like V00 first case, right? Again V10. So 10 means so this is what V1 and this is V0. Again this is what V2 means 110 and again V7. V7 means all are 11. So you just see that the first case is what A phase, A leg, otherwise B phase or maybe a B leg, and so C phase or C leg. So means for the first case, you just see that 0, 1, 1, 1 means A phase should be what? Maybe at a starting position is 0, so rest of the time is high. And from here to here it is repeated and again, so it is actually high, again it is low. So likewise, similarly for this 0, 1, 2 also. But in case of 0, 1, 2, so this one phase is what totally clamped. Just see that one phase is what 0, 1, 2 means clamped to negative side, either a negative or maybe the positive. But whereas here it is negatively clamped. Whereas 7 to 1, so the this is what clamped to what positive side. So this is actually the observation which we can able to see. And similarly for other sequences also, we can able to find that whatever may be the observations like similar to space vector PWM. Now we frame that. Whatever may be the ripple voltage vector means we resolve the vector in q axis and d axis as similar to the space vector, means so we are getting the different shapes of the dq flux ripples. Okay, so now we found that overall expression for all the cases. Okay, now we are getting the different expressions. Now after getting these all expressions, we are actually framing that different zones also. And so in which you can able to find the differences also, so that we need to find that how much differences you may get in a current ripple or maybe the THD. Okay, so this is the clamping. We already explained this. Now, so let us consider that 3 zone. We means we have been selected that 0, 1, 2 means space vector. Again, so we selected 0, 1, 2 means we have been actually we have done that means we chosen these 3 sequences, and then we found that okay, in which way the differences you can able to get. As we calculated that RMS flux ripples means whatever may be the error voltage integration, we found that error voltage integration. So with respect to the whatever may be the dt, so which is actually the function of the we used to call as we are actually dealing with the induction motor, we used to call as a flux error means flux ripple. Okay, and so now which is actually referred to the stator side. Now you just see that as we are actually following that in a open loop we have tested first, and then modulation index what 0.64 we have taken. Now as we are actually see here, this 0, 1, 2 is a green, so it's actually still operating in an upper region, so RMS flux ripple is less value, whereas SVM still is what giving means lower, means whatever maybe the range is what lower. So now coming to the, as we are changing, keep on changing that modulation index. As we are changing the modulation index, what happens? This whatever maybe the means upper side curves are coming to downside, which means that so the RMS flux value from here to here is what less for the whatever may the 0, 1, 2 sequence, and similarly from here to here it is what less for the whatever may be the 7 to 1 sequence, and from here to here so means like 10 to 0 to 10 degree, right? So the 0, 1 to 7 means this is actually the conventional space vector, or maybe the SVM is giving that lower RMS stator flux ripple, and whereas from here to 10 to 30 degree, so 0, 1 to 1 is actually giving the less value, and whereas from here to here it is giving the less value 7 to 1 sequence, and so like this fashion we have been project. So now similarly for other cases also, like we actually again you taken that some other 5 sequences. Now we operated different sequences, so even at the lower modulation index also this 1012 is what giving less value, whereas this 0121 and 71 still are at actually the same position, but somehow they are giving that less value over here, means less flux ripple. And so and similarly for a different modulation index, so right again 0.76, okay, even we gone through 0.86 also, but all are actually coming to the closer and so clumsy, so here we can able to distinguish. So that's the reason we have been chosen for this range. Even 0.86 also you will get the almost more or less same, but maybe this may be coming to the bit lower. So now, so from here to here you can able to see that differences, like again 101 is actually 1012 is coming into the picture, again 272 is also coming into the picture. So and again this 012 again 721 still continuing, which means that the area of the flux error, whatever means the RMS flux ripple is going to reduce. Means if we are now operating the whatever may the sequence in this fashion, what happens, you know, right? So we can able to improve that whatever may be the RMS flux ripple, as flux is actually as if we are actually reducing the flux ripple, right? As we are going to reduce the flux ripple, now what happens? So in sequence to that current ripple or maybe a current THD should also going to decrease. So in consequence manner, so there may be a improvement in the induction motor, there won't be any overrated, as we already seen in the some other slide. So whenever if you are having that higher amount of the THD, and so your motor is going to be overrated. So due to which you may face a lot of problems. Similarly for 7 zone we have been used, and so in which we can able to find that different sequences are going to be involved. But here one observation we can able to find that 012 is coming into the picture whenever if you are going for the 0.64 modulation index, even here also means so this is a clumping sequence. Likewise we observed, and like after observing and all, even for 7 zone also, now we actually decided that for we need to see that in which region right, like which of the 3 sequences are giving the better performance in terms of the RMS stator flux ripple. Now we just see that the whatever may be the this blue color is what conventional space vector, whereas the 3 and 5 zone and then so 7 zone, these are giving the better performance when you are moving towards the modulation index near about that whatever may be the in this range. Okay. So now, so means there is a consequent improvement whenever if you are using that multiple sequences. But however, we need to look into that also. So now, so as we found that 012 and then so 7 to 1, these are actually what dominating in the whatever maybe the modulation index is moving towards the whatever maybe the case as we see in the previous slide. Means as we are going to increase that modulation index. So now we are actually preferring these sequences as well as this conventional space vector, because this may give that better performance even at lower case also. So similarly, we have been developed the duty ratios for conventional as well as the hybrid case also. So we are actually using that D1 is equal to T1 by TS. So whatever maybe the TS actually is going to vary as whatever maybe the in case of the real-time application. So that number of variables are going to less. So it is actually a function of only this, so that you may get that pulse is actually in a better way whenever if you are actually looking at the pulse. So that what happens, so you may get that better performance whenever if you are following the duty ratio control. And similarly for the other cases also we found, and then so we found that duty ratios for all these three phases for all the sector regions for a space vector. Similarly for other cases also, like whatever may the clamping cases we have been used. But here duty ratio for C phase is 0 is because of the whatever maybe the clamp is what it is clamped to 0, and so in this case it's what 1 because it's clamped to high, right? So that's why reason you may get some differences in that. And so this way we already done that whatever maybe the RMS flux ripple as we explained. And so the comparison of the THD and also efficiency, overall efficiency, we generally follow like this fashion, as we are multiplying the torque in the output side of the motor and then speed means actual mechanical speed, then that will be the output power, and then in inverter side input side current, and then the ceiling voltage. So that way you can able to find the efficiency. Now if you are comparing the simulation results like as followed by the figures, in which we have first concentrated for the conventional case, that is what proportional integral direct torque control of induction motor under different modes of operation. So in which like we are observing that starting performance as well as transient performance as well as the step changing speed also. So for the first case, what we have given that speed command is that we have given that reference speed is what 500 RPM, and then so we need to see that what are the current performance and then torque performance, and of course speed also. Speed is also reaching to the same speed, means same value as similar to the whatever method reference speed which we have been given, and then so again we have been initiated at near about 0.5 seconds. The speed change is what 500 RPM to 1450 RPM. So that changes we have been done, and then we have gone through that what is the torque means what is the torque performance, and again so current performance and all. At starting definitely current should be what higher in order to overcome the inertia, and then so what that too we are operating in a closed loop, and so definitely so the torque controller, so this is what 20 means it's 18 Newton meters. So this is what very closer to the peak value of the torque. And so maybe peak value means maybe rated torque and peak torque is actually near about 2 to 3 times or even 4 times also. It depends upon the power rating of the machine. And so again flux, these are the distortion in between that flux, how much variation you can able to observe. And so again in the other case speed reversal, like whenever if you are changing the speed from like forward direction to reverse, again reverse direction to again forward direction, then how the things are going to be changing. Like that fashion we have been seen here. You just see that so at starting currents are higher, and as the speed is what closer to the reference value, then what happens is the actually current is going to what less is because of the whatever may be the low torque is function of that d omega m by dt. And as we know that this is actually the what 0 as the speed is maintaining constant, and so that what happens, so still we are not given any load, and the current should be what whatever maybe the current is drawing, it should be what no load current. And again if you are actually changing the speed from again 500 RPM to 1450 RPM, again we require the torque, for which again so that's where reason torque is increasing, and in proportional to that currents are also going to increase. And again after reaching to the required speed, again currents are actually whatever maybe the 3-phase currents are settled to the lower value as the no load which we have been applied. So likewise this process is going to continue, and similarly in case of speed reversal, you just see that whatever maybe the current is going to be reversed as the speed is reversing, right? So then definitely here currents are going to be reversed like a DC quantity, And again, so like how this is going to be happen, like in case of the laboratory, we are going to changing the phase sequence. So which means that currents are actually reverse. So that we are not doing by actually changing the phase sequence. That is inherently we are doing with the help of the controller, and so that with the help of the whatever the inverter control logic we have been applied, so that automatically the currents are going to changing is because of the speed command which we have been given. And here we are applying the load 4 Newton meter. Again we applied again 4 more Newton meter, and then so we observe that deceleration and acceleration takes place, and finally it is actually set to the reference value, even though if you are changing the reference speed, even though if you are changing the load. So means, but more or less it is actually maintaining that whatever may the speed is what constant. And similarly for the type 1 fuzzy controller, so even here also you'll get the more or less same performance with the whatever maybe the duty ratio controller we are using, and so there may be a slight difference in the distortion, means a slight decreasing in the distortion in the torque and flux also, and so maybe a slight variation in the whatever maybe the transient performance. Even speed fluctuations is also actually going to low, even including that whatever may be the flux distortion. So that we already tabulated. Similarly for a hybrid duty ratio controller, so as we are using that multiple sequences, so the whatever may be the distortion in the torque, and then so flux error is improving, and in addition to that, so there is slight, not big difference is there, but slight difference you can able to observe in the dynamic performance. So similarly for all these case we have been compared in the tabular column. So the whatever may the THDs also we have been compared. So anyhow, as per the IEEE means so THD more than 5% not allowed. However, we need to look into the current, and so the current THD we have been observed for all the cases. So anyhow, we are getting that lower value of the THD with the help of this whatever may be the hybrid duty ratio controller. So now, so you just see that comparison over here. So current THD comparison. So as we are changing the frequency, means the THD is what decreasing. You just see here. So the THD is what significantly decreasing. And similarly, we found that actually we calculated the efficiency as we have given the formula. So we are actually calculated the efficiency, means we have been plotted also. So there is a slight improvement in the efficiency as per the whatever may the graph which we have been given. And so this is actually the no load and full load voltage THD. So anyhow, the voltage is actually what square in nature, pulsating in nature. So in both the positive half of the cycle and negative half of the cycle, that's where reason you can expect that more amount of the THD, means it is which is actually the more than the 5% of the standard. However, we won't consider the voltage THD for comparison. So these are the current THDs for all the cases, and then overall efficiency as per the tabular column. And these are the experimental results which we have been obtained as similar to the simulation. And so we are getting that a similar operation with a little bit improved dynamic performance of the induction motor drive for the same changing of the whatever may be the reference speed and all, and then load torque for the same case. But however, we are significant improvement in the proposed advanced duty ratio controller method with the help of the 3-dimensional fuzzy controller also. So this comparison also we have been done in experimental results, and so these are the THD performance for the type 2 fuzzy, and then again duty ratio controller, and then so hybrid duty ratio controller which we have been used. And so this is what comparison of the THDs for no load and as well as the full load also we have been shown. So this is actually the again graphically we have been shown here, in which you can able to find that this hybrid duty ratio is actually giving that better performance. Means we compare that conventional one, and then so in between that type 1 fuzzy and then type 2 fuzzy, and again with that again we are actually comparing with the hybrid duty ratio controller. Means for all the cases efficiency is high, and however the THDs are considerably less. So that all we observed here, and this is a final comparative table which we have been obtained. And so like in simulation and experimental, these are the results which we are actually observed, even including the distortions also. So what less in case of the proposed system. So now overall we obtain that whatever may be the percentage of improvement. So it's actually near about this as compared to the conventional space vector PWM. So conventional whatever may be the duty ratio controller. And so now as we can see that, so for all the cases we are using that different sequences which we are going to use for driving of the induction motor. So can we use, we can use the same technique for even for a grid integration also. So how the is for grid applications also. Okay, so in the grid applications, okay, let me show one simple diagram for here. So you just see that. So here also we are using the inverter and we are working on in this direction also. We are using that inverter means definitely. So we need to we require the some PWM technique. So whatever may be the PWM technique which we have been proposed. Now in the same way if we are using, then what happens? The size of the filter which we are using here. So size of the filter is going to reduce. As the size of the filter is going to reduce, now what happens, you know, right? The cost, effective cost is going to increase. So the effective cost size is what decreasing, but the cost should also going to what decrease. And so, but inherently, so we need to look into that whatever may be the hybrid duty ratio controller, so which is going to used in the induction motor application. In the same way, even here also you can apply, and so you can able to get that better performance, better current performance with the less size of the inductor. And so capacitor, okay, of course we require that required amount of the capacitor, but still the current is actually coming to the closer to the sinusoidal with the help of this controller. And so now, okay, that's all my presentation. So if you have any queries, so you may free to ask.
Participants, if anyone have any queries, please ask.
Hello.
Yes.
Good afternoon, sir.
Yes, good afternoon.
Sir, I would like to know that can 180-degree three-phase bridge inverter be considered in category of multi-level inverter?
180-degree. So
because if
180,
we will get the Vs by 3, 2 Vs by 3 Vs. So can we say that it provides 3-level value? I mean 3-level inverter. Hence, it can be considered as a multi-level inverter. Can we technically say that?
No, what's your question? I am not getting actually.
Yeah, so three-phase 180-degree bridge inverter will give you the 3 values in the output: Vs by 3, 2 Vs by 3, and Vs, and same on the negative side.
Okay.
So can we say that it is a 3-level inverter?
So no, actually, like whenever if you are taking the pole voltages, like we need to take that any one of the reference. Okay. So if you are taking the pole voltages means like 0 minus VDC by 2, right? Again, so
Yeah.
plus VDC by 2 means so like. So we can say that whatever maybe the voltage levels, like means the steps we can able to find either a positive side or maybe the negative side. If we need to take any one of the reference, then we can say that so in general we used to call it as a 2-level inverter, which means that so we can able to observe that from 0 to top side. So how many levels are there as per related to the phase voltage? Suppose if I am telling that phase voltage, like as you said that, so 2-level inverter like VD by 3 and then so 2 VD by 3 means we can able to observe that means 2 levels. So from the reference of 0. Okay. So like even in the like 3-level inverter, if you are considering, so even in the same way for phase voltage you can observe, so you can able to get the 3-level for either side, positive side or maybe the negative side. So means we need to look into that reference. We need to take the reference so that we need to decide the levels of the inverter.
Okay, sir. One more thing. You talked about D space. I mean, you might have implemented in your hardware.
Yes.
Sir, depending on these advanced methods, what could be the limitation of D space? Because I have heard and read somewhere that if we go for high power application and the sampling could be not more than 100 microseconds. Practical approach if we are concerned about.
Yes. Actually, the advantage is that whenever if you are going for a D space, so whatever may be the MATLAB file which you are going to implement, so directly means no need to do means not require any effort. So means directly it will means give the pulses, so it will work fine. And so that is the one advantage. And then so the whatever maybe the sampling time, as you said, so 100 microseconds is actually limited, means again it is actually varying from that which type of means model you are selected. Okay, so it is actually, that is also means like 1103 is actually basic level, so there may be the limitation. But however, if you are going for the high means like 1103, and nowadays actually that that the model is changing. So I'm not able to means recalling that exact model number. So means like the limitations are there, but main thing is that in the real time is different from that actual simulation time, because simulation means okay, it will work fine, because even there also we need to specify the sampling time. So if you are maybe giving that sampling time is different, so again, so in the simulation also you will get the worst results. So the minimum thing is that sampling time should be decided in such a way that, so it should be what, so 1/6 of the whatever maybe the switching period, that should be the minimum range we need to select. So and then according to your application, that too the disadvantage is that here, so the cost is more. So because one way you are getting the directly the comparison, means so directly you are generating, but if you are going for the DSP or maybe the FPGA, means we need to actually write the coding, or maybe so for developing of the pulses, so we need to develop some programming, and then so we need to build up. So means if we are capable to do that, and of course, so again this whatever may be the system is what cost effective.
So, sir, the 1/6 of switching time that you said can be considered as a thumb rule for setting a sampling time.
Means like 1/6. Why I am telling that, like if you just look at the whatever maybe the voltages, how you are getting that 6-step waveform, right? So from that I am telling actually, so that you may get that appropriately. So at least save what we are expecting, so we may get the same value.
Okay. And sir, lastly, would you please share the material related to different SVM, SVPWM techniques? Because by far, as I honestly tell you, that I have only known the conventional SVM techniques. So
Yes.
I was unaware about the techniques that you taught us today. So would you please share the literature with us?
Sure. I will share. No problem at all. I will share. Okay, fine.
Thank you, sir.
Yes, most welcome. Yes, any other questions from the audience?
Sir, what is the maximum speed we can reach, sir, using induction motor?
So like, okay, maximum speed means okay, like if you are operating that below rated speed or maybe above rated speed, means that we need to look into that. So means maximum speed means during the time that would be a, like a flux weakening mode, right? So flux weakening mode, again there may be the limitation, like flux weakening mode. Whenever if you are operating the machine in a flux weakening mode, torque should be what is also important, right? So from which torque you are operating. Like so inherently the machine itself like having the friction, again there may be having some limitation in the friction torque also, because friction coefficient is also going to be involved in the system. So means up to that, again so the torque performance, low torque performance should be what, decrease in nature. As your speed is increasing, your torque profile should be what, a decrease, such a way that what happens, so the current whatever may be the current of the induction motor should be up to the rated value. Otherwise what happens, so current is going to be increased more value if you are maintaining the torque is constant. Even not constant also current will increase, but we should aware of the current should not be increased more than the rated value. So but in general you can go for up to even 2 to 3 times of the rated speed.
Rated. Okay.
Yes.
Thank you.
Just yes, any other
Any
questions?
more queries? Okay, I guess there are no more queries. So thank you so much, sir, for being here and sharing such an informative session. So, dear participants, we'll meet again after the lunch break at 3:15 p.m. Please be there on time. Thank you.
Thank you all.